My name is Adnan Hajomer. I'm from Technical University of Denmark. And today I would like just to share with you a recent experiment done in a collaboration with Ghent IMAC and also with Balak University. And this experiment about chip-based CVQKD. But before diving into a detail of this experiment, I would like to start by a brief introduction about CVQKD. Continuous variable are quantum mechanical observables that has a continuous spectrum. An example of continuous variable are amplitude and a phase quadrature of electromagnetic field of light. And a typical state we use in a CVQKD is a coherent state, which is basically a displaced vacuum state. And when we use it in a CVQKD, we choose this displacement, which indicated by yellow arrow, from a certain sets of possible values. These sets could have a Gaussian distribution, and this is known as a Gaussian modulated CVQKD, or it could have a uniform distribution, and this is usually used in a discrete modulated CVQKD. Okay, so in a receiver side or in Alice side, we prepare many of these states, and this we call it state ensemble, and it is characterized by some parameters called the modulation strings VM, or the modulations variance, which is basically tell you like the size of your alphabet. After we generate those states, we send it through some quantum channel, assuming to be in full control of if. And it's characterized by two parameters, the transmittance and the axis noise. At the receiver side, we decode this quantum information by using coherent detection. And coherent detections work by overlapping your quantum signal with a strong beam known as a local oscillator. And based on the phase of the local oscillator, you can detect either X quadrature or B quadrature in so-called homodyne detection, or you can detect both quadratures simultaneously in so-called heterodyne detection. The receiver side also can characterize by two parameters, the efficiency of your detectors or your receiver, and the electronic noise. After this prepare and measures phase, we do post-processing, and this includes parameter estimation, error corrections, and privacy amplification. Not necessary to be in the same orders. You can start by error corrections, and then parameter estimation, and finally, privacy amplification. Why we are interested in CVQKD? Obvious reason is it uses homodyne and heterodyne detection, which is basically a classical telecom component that can operate at the room temperature. Another benefit of CVQKD is the high rate, and also it is compatible with the photonic integration, so it can easily miniaturize the system. All right, so let's look at the first advantage, the high rate. How we can improve the key rate of a CVQKD. And in order to understand that, let's take an example, the synthetic key rate in a bit per second, which indicates the actual throughput of the system. This formula can be divided into two parts. The first part, we call it a secret key fraction, which tells us the information advantage of the of Alice and Bob over the eavesdropper, which basically is the bit in bit per symbol or the bit per channel used. And the second part is the repetition rate or the symbol rate of the system. Then in order to increase the throughput of the system or the speed of the system, you have two knobs here. The first knob is the secret key fraction, improve the secret key fraction, which is quite involved actually. Because in this case, you need either to reduce the axis noise in your system or improve the efficiency, the information reconciliation efficiency beta. The other approach is by cranking the symbol rate of the system or the repetition rate of the system, which is this one of the main advantage of CVQKD since it uses a classical telecom component. And based on that, there is a many demonstrations for a high-speed CVQKD. Here, this is not an extensive list, but this is just a selections. Most of these systems use a Gaussian modulated CVQKD. And the reason for that, because it is the most mature security proof. But if you look at the symbol rate of the system, we can see it is limited to 100 megabaud. And the reason for that, because in order to approximate the continuous Gaussian, the true continuous Gaussian distribution, it requires very high digital to analog converters and analog to digital converters, which is not available for a high speed. For that reasons, people shift a little bit to use a discrete modulated CVQ carry, where instead of using infinite number of states, we use finite numbers of states, like in a case of a QPSK signal, or in a case of a probabilistic constellation shaping quadrature amplitude modulation, which basically a discretized Gaussian distribution. Based on that, there is a significant improvement actually in terms of the speed of the system. And in last years, we demonstrate a system use a probabilistic constellation shaping that can operate at a 10 GBaud. So let's look at the third advantage, the compatibility with the photonic integrations. Although CVQ is quite compatible with the photonic integration, so far there is a single reported experiment which integrate both the transmitters and the receivers. However, this system has a limited bandwidth, and the key rate of the system is in orders of 200 megabit per second. The system also uses transmitted local oscillators, which is known to be vulnerable to the side channel, and also it uses analog-based pulse caving. And this adds additional complexity because it requires a modulators, integrate an amplitude modulators in a transmitter side. So the question here then, how we can achieve a chip-based CVQ system that can operate at a very high speed? Or in other words, what is the main ingredients in order to achieve high-speed CVQ? The first ingredient is having a fast modulators. And we achieve that by fabricating together with our collaborators in IMAC. We fabricate a silicon-based photonic integrated IQ modulators, which is basically a 2 Mach-Zehnder modulator, a nested Mach-Zehnder modulators in a big Mach-Zehnder interferometers. And the special things about this design is we added a Mach-Zehnder interferometers, this cascade small Mach-Zehnder interferometers after the big MZI. And the reason for that, this allows us to compensate for the amplitude imbalance between those two Mach-Zehnder modulators. The light is coupled to the chips through a grating, through an edge coupler. And here is on the right side, the micrograph and the BCB of our system. And here's some characterization of the system. The modulators provide a bandwidth, a 3 dB bandwidth of around 7 gigahertz. And also we can see that the frequency response of the two Mach-Zehnders modulator more or less is similar, which is quite good. The second thing we look at is the sideband suppression, which is quite important for a CVQ system. And here we investigate the sideband suppressions by tuning the last Mach-Zehnders interferometers so that we introduce amplitude imbalance between I and Q. And the best sideband suppressions we can get here is about like a 40 dB. Okay, so the second ingredient to have a high-speed integrated CVQ is to have a fast homodyne detectors. And again, we fabricated a fast homodyne detectors, which is basically a phase diverse receivers using a 2 grating coupler in order to couple the local oscillator and the signals, and a multimode interferometer to split the signals and the local oscillators to measure I and Q. And also we use some heaters in order to introduce a 90 degrees phase shift between I and Q. And also we integrate a Mach-Zehnder interferometers to balance the photodiodes. The right side shows also the micrograph of the chips, including the photonics integrated chips and also the electronic integrated transimpedance amplifier. And this chip provides a short noise limited bandwidth of around 20 gigahertz, but at 20 gigahertz we have a clearance of I think it's about less than 1 dB. The insertion loss of those two grating couplers is about 2.5 dB, and the total efficiency of the receivers is about 44%. The third ingredient is having, to have a high-speed CVQKD is having a good or efficient digital signal processing. And when we operate at a very high speed, one issue is the high frequency roll-off at the transmitter side. And this high frequency roll-off usually introduce intersymbol interference, which can violate the IID conditions. And also it can increase the access noise. Here an example of the transfer functions of the transmitters. As we can see, we have at 6 gigahertz about like a 6 dB attenuations. So in order to compensate for that, we introduce a new building block. We call it a pre-emphasis, or simply it is kind of a pre-equalization, which work by taking the inverse transfer functions of the transmitters and try to equalize the original signal. And here's the spectrums of the signals after pre-equalizations, where it can show that we have an improvement of almost a 6 dB at a high frequency. All right. So based on, we combine all these ingredients and we demonstrate 16 gigahertz chip-based CVQKD system. And in our system, the transmitters, we use an AWG operate at the 32 gigasamples, drive our IQ modulators. The biasing voltage for this IQ modulator is controlled by an automatic bias controller. And then we use some discrete component like a VOA to control the modulations variance, and also an isolator and a filter to avoid the Trojan horse attacks. As a receiver side, we couple, we use a probing station in order to couple the light into a chip to avoid the high losses. And also we use the local oscillators. Okay, so here's the DSP for the receiver side. We start by whitening filters in order to compensate for any correlation, and then we have a frequency. We estimate the frequency and a phase. We compensate for that. Then we have a time synchronization, match filtering, and finally down sampling in order to get the quantum simple. Okay, so I will go very quick through the result. First of all, we start by investigating the optimal parameters of the system. And this is done by first look at the modulations, the effect of the modulations variance on the axis noise and the key rate. And we can see that here we sweep the modulations variance from 0.3 until 1.1. And for this low modulations variance, we have a decent axis noise performance. And also in terms of a key rate here, I would like to mention here, we use a 16 QAM here for this measurement. And this arrow indicates the difference between, the difference from the true Gaussian's protocol. So as you can observe here, as you go to lower modulations variance, we are approaching to a Gaussian's performance. So this is one thing we optimize, the first thing, the modulations variance, which this result tells us we have to operate at a low modulations variance. The second thing, we look at the correlations between the speed of the system, the axis noise, and the key rate. And here, the red circle indicates the 16 QAM, while the square indicates the 64 QAM. And obviously, as the speed increases, the lower constellation does, the axis noise for the lower constellation does not increase, while for the higher constellation is increased. And the reason for that is quite obvious, because the effect of the ADC and the DACs. In terms of a key rate, we compute the average key rate in a bit per channel use, or in a bit per symbol. And as we expected, for a lower constellations, we have a lower key, while for the higher constellation, even though we have a high noise, we have a better key rate. Then in order to have like a fair comparison, or to see the effect of increasing the repetition rate on the system, we compute the normalized key rate, which means we took the highest key rate, and then we normalize all the results based on that. And even though here's the key, the secret key in a bit per channel use, in this case for a 16 QAM, is the lowest one. When we crank the symbol rate to 16 gigabaud, we improve the key rate by 60%, which is a significant improvement. So now we know exactly what the constellation we can use, which is 16 QAM, what is the modulations variant, then we demonstrate, we extend the distance into a 20 kilometers, and we achieve a finite size key about a 250 megabit per second. And in a summary, we report a record experiment of a chip-based 16 gigabaud CVQKD system. This is achieved by using a broadband integrated transmitters with photonic and electronic receivers, and also a well-designed digital signal processing for quantum state preparations and measurement. And by that, I would like to thank the team at DTU Physics and Ghent University, IMAC, and Black University. Thank you.
Thanks for the talk. Questions welcome.
Thank you for the talk and very nice work. Can you tell something about the level of security, the security proof used to extract this secret key rate that you showed? Is that secure against the most general attack?
No, this is secure against collective attack.
Collective attack with finite size effects?
Yes.
Okay, thank you.
I have a question about transmitter's IQ modulator. So I understand that receivers optics should be done as low loss as possible. But for transmitter, what is motivation to make a custom solution instead of using like off-the-shelf telecom one, which tens of gigahertz, like 40 gigahertz is available? And
actually, this is a great question. And I can answer these questions from a different perspective. First of all, what is the limiting factor for the speed? Why we need why not to go to a 20 gigahertz or a 30 gigahertz for a CVQKD? Because as I said, it's compatible with the classical telecom. And the limiting factor is not the transmitter side. You are true. We can use like a standard off-the-shelf IQ modulators from a telecom, but it's the receiver side. It is very hard to get a receivers with a very high bandwidth, and it can provide a short noise limited bandwidth. So these are limiting factors for a CVQKD. But you are true. We can also go for a commercial system.
A very nice talk. I saw some. I see your diagram S21. That a 3dB bandwidth is almost 7 gigahertz, but your
sorry, I can't hear you.
Transition speed.
It's not clear for me, like what you are saying.
Okay. Your 3dB bandwidth is almost 7 gigahertz. But you do experiments that getting speed at 8 to 16 GBaud, and I get some confused. Why this relatively low bandwidth can lead to such high speed?
Okay, so the question, if I understand it correctly, I'm operating at 16 gigahertz. And I have a 3dB bandwidth of 7 gigahertz. This is exactly what I explained when.
Yes.
Yes. This is exactly what I explained. The actual bandwidth, if we look at the 6 dB bandwidth, is about like 16 or more than 16 gigahertz. And this is why we need this period equalizer in order to compensate for the high roll of frequency. So this is basically the enabling factor to operate at this high rate, even though the 3 dB bandwidth is just only a 7 gigahertz.
Okay, thank you.
Okay, if there is no other questions, let us thank the speaker again. Thank you.